coming. I asked Raphael to give me the first part of the lecture just so that I have time to actually go over cross-validation with you, because some have already noticed it's part of the homework. And I also think it's just a really important concept that everybody should understand. So just for a short repetition, so we are all on the same page again. We had the k nearest neighbors classifier, right? And we were discussing how to evaluate the choice of k, right? K was the number of neighbors we look at to determine the label of a new data point we see. So this was the first attempt, basically computing the accuracy for a given k, and then your data x and your label y. And it's training the classifier here and then doing the predictions. And it's doing the predictions on the data it also trained on. And then what we saw in the plot, right? So we did this for k between 1 and 50, and we saw this plot here. And we said it has really, really high accuracy for k equals 1. Does someone remember why? Why is the accuracy up there 1? Exactly, because I'm testing on the same points I trained the classifier with. And k is 1, so there is no misclassification on the training set, right? So those two conditions make my accuracy 1 here. And then we said this is actually not that useful. What we really want is to test the performance of k for new unseen data. So we simulate new unseen data by splitting our data now. And this is what we call a validation set. Validation set because we validate in order to tune the parameter k. We're kind of still training, right? There's one part where we really fit the classifier to the data points. And then there's another part that I now use to obtain the optimal value for k. This could still be considered part of training the classifier. This is not testing. And this is the concept that I want everybody here to really understand. So here now we have a validation set. What changed is I now split the data here. And you see, again, we have a convenient function. And this says train test split. I actually think that's a bit unfortunate, but I can't change the naming that the scikit-learn people chose. Because in this case, you see here, I name my variables that this is a validation set. So in my mind, this is not a test set, although the function here says train test. This is going to become more obvious even later what I mean by that. So just for now, accept that the naming here says test, but what we really obtain here is the split for the validation set. All that this function really does is it splits your data randomly into 2 sets, right? And this number here says what proportion goes into which. So the test size is 1/3 now of my original data set. So I take my original data and I split it into 2 subsets. One is 2/3, that's my training set, and one is 1/3, and in this case, this is my validation set. And now we fit the classifier to the training data here, and we do the prediction on the validation data. This is different from what we did before, right? Now the predictions are on a data set that the classifier hasn't seen before. That is the big difference here. And then we just return the accuracy score for the predictions on the validation set. And we do the same as before. We just compute the values and append them into a list and plot them here. And you see that actually the opposite happens, right? This is my training curve that I had before, right? Accuracy of 1 for k equals 1. And you can see now that I used the validation set, it tells a completely different story. Now k equals 1 actually has the worst performance, right? My accuracy really, really dropped here. And then it goes up. And then it kind of goes down again. So can somebody remember what causes this drop here? Overfitting, yes. And what overfitting looked like, didn't I have this plot here, right? this is what overfitting looks like. I have a small island here that is brown, emitting of all the blue 0 class, right? I think the brown guys are 8s here. So this was our digit recognition data set. And maybe that was just noise, right? Or a really weird 8, something that doesn't happen that often. But you can see that island around this point here is quite large. So if by chance from the validation set points end up in this little island, they're going to be classified as 8s, even though they're really 0s. Let me go back. Okay, and then this is kind of typical that you have your range where k is reasonable, and then the performance decreases again. And this is where I start to smooth too much, right? We said k has the smoothing effect. Like my decision boundary gets less wiggly. But the smoothing also means if the real decision boundary actually has some wiggle room in there, I can't model that anymore. I can't capture that because I smoothed so much over it. And this is where my performance decreases again. So we want to find a sweet spot here for k. So overfitting in general is worse if you have very, very flexible models, right? If I have k for k nearest neighbors, if I have my k really small, then I get this really wiggly decision line. We're going to have different classifiers later, and you can, yeah, a lot of classifiers have a parameter that you can tune to say how much wiggle room you allow for that decision boundary. And it's very typical that you obtain this low training error and then a high prediction error if overfitting occurs. Overfitting means I fit really, really well to my training data. I fit so well that I start to capture noise. You can think of it as noise in this training data, and this messes up my predictions later on. And countermeasures are regularization. I already said that a couple of times. Where is this in k nearest neighbors? What is my regularization in k nearest neighbors? Come on, you know that. K nearest neighbors, my classifier. What does regularization mean? If I regularize, I give it less degrees of freedom. I give less wiggle room. So what do I use? K, yeah. It's just the smoothing. Regularization only is just a form of smoothing here. So if I make k larger, I regularize my decision boundary, I smooth over it, and that prevents overfitting. And the other thing we do is we use cross-validation, because as you have seen, if you really need this validation set to capture this effect, right? If I would just always make predictions on my training set, I would not only have chosen the wrong k, I also would have been overly optimistic about my classifier performance. If I would have actually optimized k, I would have chosen k1, and would have reported, hey, I can classify everything out there correctly, which is not true at all. And on the other end, you've seen that the training curve was always, the accuracy was over the validation curve, right? The accuracy was better. And this is also very typically. Normally, you perform better on your training set, which makes sense. It's the data that the classifier has seen, right? It shouldn't mess up those. So if you just report training error, in most cases, you are too optimistic about your actual performance. Okay, I just need that. Okay, now we go one step further. So in the previous example, I only split my data into two subsets. One was the training set, and the other one was the validation set that I used to tune k. But if you have a customer, as a data scientist out there, that customer doesn't necessarily want to know which k you chose, right? Most of the time, they don't want to hear anything about your classifiers at all. They just want your score. They're interested in how well are you doing. If I give you new data, what is your performance, right? That's what they want to know. And they want to know this for new data. Now, before we had our training set, we can't report a score on that because the classifier has seen it. Now, we also shouldn't report the scores just on the validation set. Why not? That's a bit more tricky.
Because you chose use that to pick a k?
Yes, Exactly. So we had our training set to fit the classifier, and we have our validation set to compute the optimal value of k. This is tuning a hyperparameter, and this can still be considered part of training. And you are still going to report slightly too optimistic values then, if you just use the validation set. So what you should do is you should have a third split of your data with your actual test data. And that data should be absolutely new. Like, none of the actual training, parameter tuning, validation should have anything to do with the test set. So what you normally do is right in the beginning, when somebody comes to you and says, here's the data, you don't do anything, you just put the test set aside. If you want to do a publication later or something like this, or you need to report to a customer who paid you money, you really want to report a test score. So in most cases, you can't actually go to your customer and say, yeah, now give me new data, right? I used everything to train my classifier. Please now give me new data, and then I can tell you how well I perform. So we try to simulate that by putting this data aside right in the beginning. This is also in the homeworks. So in homework 3, problems 2 and 3 are the machine learning assignments. They're actually, by design, quite easy. Like, it's really about getting into scikit-learn and learning those functions. And the first part there is split your data. And then the next part is do a scatter plot. And so normally, which data would you plot from now on? What? The test data? No, you split your data. In the beginning, it says split your data into train and test. And then the next part is do a scatter plot. Which data do you use for the scatter plot? Yes, the training data normally. If you want to be absolutely 100% accurate with this, the test data you never ever look at. Because otherwise it's also tempting, right? You see it in the scatter plot and you go like, oh, there are some outliers here. Maybe I should handle those differently, or something like this. If you are really 100% correct, you put that test data aside and you don't do anything with it until somebody asks you for your final performance score. And I know someone who worked at BBN, and he actually told me they're so correct about this. If a customer in between asked for a test score for whatever reason or they need it, they compute it, and afterwards that test data, even if it's only been seen once, goes into the training pool. And then they have to have additional test sets later on to use. So whenever they report a test score, it's truly data that the classifier and even the guy programming it most probably has never seen before, to make absolutely sure that this is real prediction performance. Okay, so in the problem assignments, of course, I'm not that strict, right? You're welcome to do the scatter plot on both if you've already started with that and done that. Just so when you know for your final projects, or if you take a job in data science or whatever, the test set, first thing you do, test set aside. Don't look at it again. So now cross-validation then has these 3 subsets. I said train, validation, test. Now please, I actually was shocked. I looked at the scikit-learn documentation, and this validation set terminology is not out there so much as I thought it would be. This is really standard in machine learning. But some people, when they say validation, they actually mean test. So you have to be a bit careful in what you read, right? What they use it for, and what they report, and what they use for parameter tuning in their sets. So for this course and for our terminology, it's train, validation for the hyperparameters, and then test. Do you have questions about this? About the splitting? Yeah, I think in the homeworks it actually says how much. What? Oh, sorry. The question is, what is the percentage you normally should split for train, validation, and test data, right? So for the homeworks, I think I give you the number. In general, it depends a bit on what your data size is. If you have a lot of data and you can afford it, you can actually do a 50-50 split. But normally you would still want to split your train data further into train and validation, right? So then you can also do just 1/3 for testing. That's quite common, or 20% for testing. These are the most common things people use. It depends a bit on how large your training set is. Not training, your original data set before you split anything. Well, that's a good question. So there's really, in my mind, only one reason where you do not need a validation set. What is that reason? Can you think of one? Yes. For me, in my mind, that's the only argument you have for not using a validation set. You're not tuning anything. Now, some people actually would not tune K. It would just drop out of the sky, is what we say in papers, right? Some parameters just drop out of the sky. They just go, yeah, I think it's 3. That's fine then too, but no, actually that's not fine. You should really tune your parameters, please. So for that, the validation set is necessary, and the only scenario where you do not need a validation set if there is nothing to tune. So why do we actually need a training and a validation set? That is just recap. Overfitting, yes, we want to avoid overfitting. You've seen before, if I only have the train and the validation set in one, it's like tuning K on the training set, right? We've seen that. That means K equals 1 is the best solution. And I already said, why do we need the extra test set? It's because if you would report on the validation set, you would be still slightly too optimistic, right? Because you used it for the tuning, so you used it for part of the training. So totally different question. Why would Raphael be upset with my plot so far? I'm not asking him, I'm asking you. There's a big, big difference between all the nice plots Raphael showed before and the one I just kind of screwed up. Actually, there should be 2 reasons. Right? I mean the cross-validation plot of the training and the test performance, this guy here. There are 2 things wrong with this. One, I actually just realized last lecture, and I'm sorry I didn't fix it. Does someone remember?
Discrete values.
Yes, K has discrete values, so the line plot here wasn't the optimal choice. What is the other thing that I should fix? Oh, okay, yeah, okay. That's not what I meant. Like, if you remember Raphael's things he showed, did he ever have just a straight line? He always showed box plots, right? Well, what am I not showing? Yes, thank you. The error. It's just a line. There's no standard deviation here, nothing. So let's fix that. This is another rule. So one was, this is about working in a clean manner. Like in my group where I did my PhD, there were 2 rules. One is always cross-validation, always have a validation set, never look at your test set. And the other rule was measurements without error bars do not exist. So when you do evaluations for your final projects, please, we always want to see error bars. So how do we get the error bar? Is we can just split the data multiple times, right, and do the computation over and over again. And this is exactly what I did here, and I did the same mistake about the line again, but now I have a standard deviation here. It's actually interesting because here, this plots the mean, right, and the standard deviation, so I could kind of say, oh, K4 seems to be kind of a nice choice. So you see here, I just do multiple splits here of the data. I just do the No, where is it? Random seeds, randoms. Oh, I use my function here. This accuracy for k-val. It's actually a bit more complicated than it should be, maybe. I'm giving it different random seeds here to get different values. But that's all that happens here. I do multiple random splits of the same data. And then I just tried to fix that, and I actually was surprised. So this is normally for a discrete value, maybe what you would show, right? So these are box plots. And this nice effect for K4 is actually gone, because box plots show you the median and not the mean, right? So I thought this was actually interesting. I just did this 30 seconds ago before the lecture and was like, oh, now it's actually not so nice visible anymore. So that's interesting. But this was probably normally the type of plot you would want to have. And I like these box plots because the colors and everything, I think the defaults are quite nice. And this is Seaborn. This is also in the homeworks just that I mentioned this library, and I think it's quite nice for statistical plots. Okay, but there's one last thing just that I want to cover, and that is k-fold cross-validation. So I said before we did cross-validation, was just splitting our data, right? Now we're doing folds. And these folds, what it means is if you take 20% of your data set, these are only 4, but imagine a 5th here, you take 20% of your data set and say, this is my test data. Yeah, I think in this here it's test. So you would take 20% of your data set and say, that is my test data. And you do that 5 times. So you have this chunk of data here, right? And then you have another chunk of data, and this is always 20%. So you have 5 different folds, and in each fold, the data you use for testing is 20%, and the different folds here are disjunct. This does not happen if I just randomly split my data, right? Then I can end up with the same data points in my test set again. And this is not happening here. So in this case, I have 5 different splits. And the test chunk basically gets shifted around and covers, in the end, the whole data set. It's still test error, because what happens is I have to fit my model 5 times. So I can't just train the model and then 5 times compute an accuracy score, right? What happens instead is I train my model, I predict the test error, I train my model again, I predict the test error. Now, I just stole this figure and just have the test and the training in there. Where would our validation set be here? In gray or in white? White, yes. This is our training set here, and the validation set is part of the training. So you could, inside this guy here, do again k-fold cross-validation, right? You could take this chunk out here and have a little validation set here, slide over, and have like 3 folds maybe or something. So with this method, I can get 5 different scores from the same set and still do kind of training on the whole data. So if you don't have that much training data, this is a way out of that misery. Any questions for k-fold cross-validations? That should be clear because that is in the homeworks. So please, if you have questions. Yes?
Isn't the point of doing these experiments over and over again so that you can test a constant k? So why would you need a validation set to begin with? Wouldn't you just need test and training?
So that you can test a constant. Well, how would you choose k?
Looking for a standard deviation for each value of k.
Yeah.
Presumably, when we repeat these trials, we're holding k constant for control.
So if you would.
Why need to validate?
If you would do real, if you have enough data, one option actually is that you tune also k for each of these. You can do that. If you would write a machine learning paper and go like my method is really great, right? Then it would be okay to tune the K, but you would need to do this with the training set. And then you compute the test scores here, and you have 5 different test scores for 5 different models, basically, that you fitted 5 times, right? But then the K would be allowed to differ for each of these. Are you asking with respect to the homework? What did I do? Training and validation. I think in the homework I actually asked you explicitly to report the test error for the case. So then if I explicitly ask for that, then you can compute the test error there. But normally this, for each fold, K would not necessarily have to be constant. Because what you're simulating is that you're not seeing this data here. And this data here shifts over. So which data chunk would you use to optimize K? Right? You would have to choose a data chunk that is not ever covered by the test set. And in the K-fold cross-validation, that doesn't happen. I think that's the, does that answer your question? Okay. Different questions? Then I'm done. So I'm not sure how this works with Blackboard. Do I log out? Do I just stay in? If we switch over? You did this before with Mark, right? What did you do?
I don't have I didn't put the thing on the web yet. Maybe that's faster. I'm going to put the HTML.
Do you need a few more minutes? Because then I go on about invariance and classifiers. Okay, let me do this. This was just something neat that I wanted to show you. Remember the k-nearest neighbor, so cross-validation is over. This was just an addition I had for the k-nearest neighbor classifier because I thought it was a nice illustration of something that works for other classifiers out there as well. So we have digit recognition, right? We had 0s and 8s and 1s, handwritten digits, and we wanted to classify them. And if you think about that a bit more, we just had this little patch, right? We showed those patches, and the little digit was inside. But if that 0 or even that 1 is just shifted 1 pixel to the right, or even 2 or 3 pixels to the right, it still stays a 1, right? But it would be a different data point in our feature space. You said each pixel is a dimension, right? So I have one data point that represents a 1 in the middle, right? Just a straight line. Then I have a different data point that represents a 1 that is shifted by 1 pixel only. It's going to end up somewhere entirely else in the feature space. So, but it's still a 1, and this is what we call its translation invariant, right? If I shift my 1 inside that image patch, it doesn't matter for the classification. And to a certain extent, it's also rotation invariant, right? If somebody's hectic, I wouldn't insist on something being really orthogonal to be a 1. Maybe it's a bit slanted. It's still a 1. So to a certain degree, we also want rotation invariance in the classifier. And there are methods that you can use that work with other classifiers as well to make them, to address these invariances. And one is to just add the transformation to the training data. That's the easiest, right? What I do is I compute translations of all my digits, right? I take that image patch with 1 and use my favorite image processing library and shift it by 1 and just add that patch also to the training data. This is still done a lot out there. What is the drawback of that method? What is the negative part if I do that? Especially for my k-nearest neighbor classifier.
It's not, might not be the right label for every single translation, would it?
That's actually a good point. That is why it's only to a certain extent rotation invariant, right? If I rotate a 6 too much, it becomes a 9. So yes, the label may change. So let's say we make really sure that we don't go overboard with our transformations, and it's still a 1 in there, and it's still a 6, even though we rotate it. But we apply all these transformations and add all the data points to our training set. What do we say k-nearest neighbors has problems with? Yes, it's computationally very expensive. If I add all those data points to my training set, it's going to explode, right? So it gets even more computationally intensive. So, but it's a way to handle things. Another way is to introduce a canonical representation. Instead of rotating my 1, right, by various types of degrees, I can instead pre-compute all my digits, try to find, maybe do SVD, find 2 principal component axes, right, and try to align them all that they're nice and straight. That's a different option I have. And now I forgot which is the third on there. Great. Other transformation I have adding to my data set. Oh, you could put it into the distance metric, right? You could try and actually go in there and try to have your prior knowledge reflect that distance metric you use for k-nearest neighbors and make that invariant to those rotations and shifts. That is computationally the best option most probably, but it's also the one that is going to be most complicated. Yes?
Is it kind of unfair? I mean, it's not really a new data point, so aren't you kind of overfitting a little bit? Because if someone were to draw 3 a little bit over, it might not look exactly like the fit you already have. So if you don't have 2 data points, you have like 1.5 data points or something. Or like some way, it's not quite as good as the new data point, or is it?
Normally, I think you handle it as, yeah, you just go, if you would have drawn it the other way, like if you wouldn't have known and it would have been the other way around, you would still have assumed that it's the same valid 3 as the others you got, right? So in this case, I wouldn't put a different weight on the ones you transformed. There are other transformations you can do, and then you can think about reweighting things. But in this case, I would just go with the transformation to an extent that I still would have thought a human could have come up with those. But this trick of just adding, this is the simplest one, right? Just adding these different data points to a classifier that also works with other classifiers. How are you?
Yeah.
Great.
Okay, thanks. No, it's there.
Oh, you're using my computer?
Yeah.
Ah. Wait.
Thanks. So I want to comment on the question about how to do cross-validation, because there is no obvious rule of thumb. And one thing that I think is also important is that if you make your training set too small, so if you have it, for example, that could make the problem you're solving different enough from the actual problem that it won't fit the best model. So see what I'm saying? So if you have if your data set has 1,000 outcomes, and you train on a data set that has 500, now you might make a choice that will not work as well when you go back to 1,000. So my preference is try to get as close as possible to that, but at the same time, without making it too small, the test set, that you'll make mistakes on that side. So so that makes it hard. But in a big data set, I tend to use 90-10 in a big one. So if you do 90-10, you can have 10. You can have 10 data sets that make up the big one, and then you do it 10 times. That's just another approach. Okay, so today I want to cover a very important. Maybe won't mess with topic that is. It's dangerous if you don't know what I'm talking about today, and you become a data scientist. You'll see you're already seeing the problems of having people analyze data without being aware of some of the caveats that come with analyzing data. And I think the most important one to know about is confounding. So I'm going to talk about that today, and yeah, that'll probably be all I talk about. So last time, and in this homework, you're going to get this data set where you have runs and singles and home runs and doubles, all this data for the baseball homework exercise. And one of the things we noticed last time that we talked about this data set is that if you look at the correlation between between base on balls and runs per game, it's higher than singles and runs per game, which is it's a little bit counterintuitive that two outcomes that have the same result, you get to first base, would be correlated so differently with runs. And in fact, those that know enough baseball know that the single should actually be intuitively sounds like it should be a more important outcome because you can actually score someone from second base. That's a technicality, but at the very worst, they should be the same. And that's not what we see. Right? We see that bases on balls, if you just do correlation with runs, it has a higher correlation. So is that really something that we expect to happen? So any ideas of what could be explaining this? Any explanations? Anybody want to give their opinion? Yeah. Say that again? Oh, the singles occur so frequently. No, singles and base on balls are of similar frequency, yeah? Okay, so that's a possibility. It might be that the high base on balls means that your pitcher is out of whack or getting tired. So anybody else? That is another possibility. That's arguing for this being actually true, that this relationship is something real, that baseball caused more runs than singles. But here's my interpretation of that data. Someone that hits a lot of home runs, like the home run is the one where you go all the way around and score a run. Someone that hits a lot of home runs, the pitcher is going to be afraid of. They don't want them to hit. They might not want them to hit the ball because if they do hit it, they're afraid it'll be a home run, so they're willing to let them go to first base. And this is corroborated by this picture. People who hit a lot of home runs, it correlates with teams. This is teams. Teams that hit a lot of home runs also walk often. Right, so one possibility is that the reason walks are correlated with runs is through the home runs, not just on their own. Okay, everybody see that? So that's called, in science, we call that confounding. So here's, whoops, there's a picture okay, so here's a picture here's a type of analysis you can do to check for this. And you want to be doing this when you're worried about such things. So here what I'm going to do now is I'm going to take each team and I'm going to split teams by how many home runs they hit. And I'm going to split them into 10 groups. There's a group that hit the fewest, the 10% fewest, and then the highest 90% is at the end. So it goes 10, 20, 30, 40, 50%. So 0 to 10, 10 to 20, 20 to 30. That's the pattern. Okay? And then and then within these groups, I'm making a plot of base on balls, runs versus base on balls. So now the home run argument is going to go away a little bit because now we can't say it's that home runs cause more base on balls, which and also cause more runs because we've stratified to teams with about the same number of home runs. Okay, get that the idea? That's a very powerful idea and technique to check for these things. We're going to do it again later. Now we do that, and you guys see the pattern. You can see the confounding. How can you see the confounding? What is it about these pictures that show you that there's confounding? Well, that's okay. So that's the correlation decreased. It used to be like 0.55, and now we see correlations around 0.3, which is more 0.3, 0.4, which is more like the singles. So now in this plot, they do look like singles. But the other thing you see is that home runs is definitely correlated with runs. You see that? See how the cloud moves up every time? The cloud moves up. That's because the more home runs, the more runs. And we've stratified to have the home run hitting teams down there and the non-home run hitting teams down there and the home run hitting teams this way. But the other thing you see is that the cloud shifts from left to right, which is also something we expected. That means teams that hit a lot of home runs also walk more. But the main point of this picture is once you stratify teams by home runs, the effect of base on balls is greatly decreased. It's not gone, but it's more like a single now. So let's go back to this slide. So here, when you read studies, you read the news and they find that people who hit their kids, the kids end up in jail more often. Right? You see papers like this in the newspaper, and there's academic papers that show this. And if you think about this for a little while, you're immediately start thinking of alternative explanations that would. It's not the hitting that makes them criminals. It's something else. You could look at socioeconomical status. You could look at age of the parents, a bunch of other stuff. So many times when you see these, and there's many other examples that you could you talk about. Like does alcohol, if you correlated alcohol and cancer in the 50s, it would correlate highly, but it was mainly because people who drank also smoked. So it's the same kind of problem. So when in epidemiology, the most common way to try to adjust, I put adjust in quotes because it's a model assumption that might not be right, is to include in a regression model the two outcomes. So in our case, if we fit a model that only has base on balls, it tells us that every base on ball gains you 0.75 runs. Right? For every extra base on ball you get 0.7 more runs throughout a season. That's what the regression model gives you with just those two. But if I now include a regression model that has both bases on balls and home runs, like we did in the previous lecture where we look for the least squares estimate with a model that has both of them, the coefficient for base on balls drops almost half. So it's still there, but now we say we adjust it for home runs, and now the effect is not as great. So this is a very common technique that is used in many of these studies that have possible confounders, like the two examples I just gave. They will fit a model that tries to adjust for possible confounders using regression. Now, I want you guys to think about what it means to do it this way. For this to work properly, the model has to be right. The model that you fit has to actually be the right model. Otherwise, you're not necessarily adjusting the way you think of. So the main point is this is a widely used approach, but I personally think for adjusting that it's not a magical approach, and you really have to test it out, do diagnostics to make sure that it's doing the right thing. I think in this case, it's probably okay. In this particular case. We can talk more about that later. Okay, so that brings us to the topic of the day, the message of the day, which is that association is not causation. This is related to confounding. So here's an example, a funny one. This is the divorce rate in Maine. The correlation with the per capita consumption of margarine is about 0.995. Right, so that's based on real data. And you can see that this has one of those two axes things that we shouldn't be using. I just got this from a web page. And you can see a very, very, very strong correlation. This particular example, unless you believe that maybe somehow the two are related, is probably just a case of it's just a statistical fluke that you just happen to get. It just happened by chance. Even though it's super strong, if you're looking across many examples, you'll find some. So here's another one that has a confounder as an explanation. So the U.S. spending on science is highly, highly correlated with suicides by hanging, strangulation, and suffocation. So do we continue funding science, or do we save people from strangulation? Well, so what is it? This is an example where the explanation for this is quite simple, and it's the confounder. What's the confounder, you think? Well, one possible confounder that could explain this. Nobody? No ideas? What could it be? One possibility, simple one. So I would say it's just population growth. Population growth, and there's more money, there's more collection of taxes, there's more money to spend in science. And then also the rates are probably fixed for this type of death, but the population's growing, so it's going up. So there's a lot you can do. There's a lot you can find that are basically just based on population growth. Okay, so there's a bunch more. You can see this kind of funny web page, and you can vote for your favorite. This is a person that just dedicates themselves to finding these things. This is a funny one. So definitely, I would say Nick Cage should definitely stop making movies, regardless of swimming pools. There's another funny one. That's another. The tangling thing comes up often. Margarine, I showed you that one. Anyway, so you can see many funny ones, and these are showing up high because people upvote them. You can go and upvote the results. But most of the ones you see here are just spurious, like he's just picking them because they data mining through a bunch of them and picking the ones that some of them are clearly confounding. So here's more examples. These are more serious ones, and now we're getting into policy that you can you can make big mistakes if you don't think this through. So if you just base it on data, the first one's kind of obvious. The more firemen you send to a fire, the more damage is done. So that's a fact. You can look at data and look at it and see that it's true. So do we stop sending firemen to fires? Obviously not. So this is another type of confound. It's not really confounding. This is another type of error, which is confusing cause and effect. It's a bigger fire. I guess you could say they're both confounded with big fires. Big fire does more damage and brings more firemen. The second one is also, I think, a cause and effect reversal. Children who get tutored get worse grades than children who do not get tutored. Right, so there was a New York Times article on a similar topic that was recommending, I couldn't believe they published this. They were recommending, although in their defense it wasn't an article, it was an opinion piece, but they were recommending that you shouldn't help your kids with the homeworks. And it was basically making that argument. They studied data, and they noticed that students that got help from their parents in their homeworks did worse than those that didn't. And I think that's the reason, is that you're confounding it with the children who don't do well in tests. Those are the ones that need tutoring, and they're the ones that get tutoring. Now, the third one is a clear example of confounding. Take a moment to read it. So astrological sign is correlated with IQ, and then it goes away. So what's the confounder there? Assuming you don't believe in astrological signs, I'm a Virgo, so that would make me very dumb. Because according to this study. So what is it? What's the confounder? Go ahead. Age, yeah. So when you're young, the difference between someone born in September and someone born in August is 20%. 20% difference in age in kindergarten. When you're in college, it's only like, point something percent. Okay, so those are examples of that's a good example of confounding. It's confounded with age. Same goes for shoe size, right? In school, if you go to elementary school, shoe size is correlated with IQ. Do you see why that is? Like the little kids have smaller feet than the 8th graders. Okay, so that's again confounding. Okay, so now let's look at a real example that caused a lot of controversy in the 70s, I think, in Berkeley. And I think this is an important example because it relates to a topic where at least I think there is some need for improvement and less prejudice. But if we don't attack if we attack the wrong culprits, then we do more harm than good. So when we go through the example, I think you'll understand what I mean by that. So here's some data. This is all real data. This is none of this is made up. You can get the data and look at it yourself. So in 1973, in graduate admissions in Berkeley, 44% of the men were admitted compared to 30% of women. All right, there's a table. You can look at it for a little bit and see that it in fact is very concerning. If you try to figure out what's the chance of that happening if I'm just assigning males accepted and rejected by chance without without looking at male or female, the probability of it happening by chance is less than 1 in a billion. So the data certainly points to a problem if you just look at the data. Okay, now, so that was, I think there was a lawsuit that was filed because of that result. But then, when I guess Berkeley was defending themselves, they show this table. So here are the percentage admission rates, percentages, split up by majors. So take a look at that for a second, and tell me what the contradiction is. It's pretty clear, right, that there's something funky going on. So here are the percentages if you take all the cases, and here's when you split it up. So when you do it all, it looks like there's a strong bias against women. When you look by major, there's a slight bias in favor of. If you look, well, I guess it'll take you a while to do it, but there's a slight edge for females when you look at it by major. So what's going on? You already see what it is? What is it?
One of the majors is really large.
And how does that matter?
That it's taking though a slightly larger percentage of men, a lot larger number.
So you don't know that yet, but that's right. You haven't seen that yet, but there's an easy major, right? You see that there's an easy major and there's a hard one. So F, physics, just kidding, is a hard one, and A, who can I make fun of? Anthropology? I don't know. Is an easy one. But this is a fact, right? There's graduate programs that are many people, others that are hard. So here's now getting to what you were saying. So here's a picture showing what's confounding. So this, by the way, is called Simpson's paradox. It happens in many situations where when you look at the aggregate, it looks one way, and when you split it up into groups, it looks the other way. So here, look at this figure, and now you're going to see what's going on. And it's exactly what you were saying. So look at the easy major. There's a major that lets 70% of people in. And look who's applying to that major more than another group. You see the confounding? So if you follow, the ones are the males. And you look at the percentage that gets in, you can see that they tend to go for the easy majors. You see how it grows? The easier the major, the more men apply. Everybody see it? It's kind of growing up. Now women are not like that. It's kind of spread. So here's a graphical view of this issue. So you have what I've done in this picture is I put everybody, all the people who applied, I put them up there, and in green I assigned. This is basically the same picture you just saw, but it's visually maybe a little bit easier to see. Green is you got accepted. Orange is that you did not. So you can already see that males are accepted at a higher rate than females when you look at everybody. Now, if you look closely at that figure, you can see A's, B's, C's, and F's. It's almost impossible to see it here. But if I split them by major, then you really see this. It really strikes you what's going on. So look at the A, B majors. They're emitting about the same percentages, but there's way more males applying, and that's the one that's easy. So there's a lot of green in A and B overall, and way more males. And if you go up to the hardest one, F, it's slightly the opposite. But one by one, the rates are about the same. So there's the confounding. Okay, so if we use this regression idea, what we would do, the equivalent thing here would to take the differences within major, and if you do that, then I don't think that's even a significant difference. But the observed difference, the average, so you take the average of the first major, you average the differences major by major, the average is 3.5 higher for women. So this is, again, a very important, just a way of thinking if you're going to be a data scientist. When you see a result, and especially if you're going to be in the social science, if you're going to be working in the social sciences where the data implies some kind of what could be interpreted as a causation effect, you really want to be thinking about what other possible hidden variables you haven't looked at may affect your results. So in general, when you have observational data, this is going to be an issue. This could be an issue. In clinical trials and other similar experiments, you get to randomize. So if we were going to do this experiment, we would have randomized applications. Just change the sex by chance, send them to Berkeley, and then we would get a result back. Then any differences we would see could not be explained by some other alternative explanation. But in observational studies, you don't get to do that. In for example, smoking and cancer, that relationship has never really been shown physiologically, biologically. It's all data-driven. It's all observational study-driven. And at the early days, when epidemiologists were starting to point this out, the tobacco companies were strongly fighting it, and they kept claiming there was confounding. It was confounded with this, confounded with that. It's not really cigarettes, it's something else. In fact, the last claim that finally was killed, there was a gene that made you both want someone that likes to smoke and someone that gets cancer. That was their last claim. That's a hard one to disprove. You know how they did it? How they disproved that one? Any ideas? They looked at twins. So they had twins. One of them smoked, the other one didn't. And again, that took a while to do because you needed twins that were discordant in their smoking habits, and you needed to wait for them. You need to follow them until some of these people had got cancer, and no, I guess you could do it retrospectively, but eventually they found that there was still an association, and that pretty much put it to death. But you can still keep making claims about confounding. All right, so that's the important lesson that I'm hoping you take, and always think, what are possible confounders? So one thing you can start doing is reading the newspaper, and when you find one, share it with Piazza, because they're all over the news, these examples of confounding. Okay. So I don't know, should I start the next lecture or just wait? Should just wait. We're too close. What do you say? Start? End. All right, end. All right, well, I think I'm going to stop and take questions instead of starting the next part. Any questions? Anybody wants to share an example of confounding that is funny or interesting?
XKCD and correlation.
Which is that one?
XKCD and correlation.
Well, one of my favorites of all times is, this was an article in the San Francisco Chronicle. What I said? X? So there was one article in the San Francisco Chronicle that claimed that screaming to your children made them eat more. And I, being a kid that liked Cheetos a lot, knows what was going on. Because when I had like my big bag of Cheetos and eating nonstop, my mom would scream, "Stop eating Cheetos!" So that was the cause. That's why I got a little overweight. Okay, so let's see. Okay, right. Don't get mad on me. Okay. All right. Any questions? Any other questions or comments? All right. Okay.